Yeah, we are good to go.
Okay, thank you for the invitation. And so actually today I'm going to present this exact derivation of quantum mechanics from classical relativistic physics as the manifestation of a cyclic nature of time. Well, okay, I must present my results as they are in my paper, and they are extraordinary results because actually I have a full mathematical unification between classical ultrafast harmonic mechanics, that is a particular subclass of classical mechanics, and ordinary quantum mechanics. This is not a conjecture because I have a long row, many full exact mathematical demonstration of this equivalence. And for instance, it is proven for general physical Hamiltonian system for in terms of canonical quantization, for a single degrees of freedom in terms of Feynman quantization, and for finite degrees of freedom for the second quantization. And as a confirmation that in physics, good results never come alone, I have also something interesting here because I have a unified description of gauge interaction, gravitational interaction, both from the principle of general covariance. And all this has been also tested in non-trivial quantum phenomena, such as Josephson effect or others. All this must be taken seriously because it is the subject of at least 20 publications, and many of them are in good academic journals, such as Annals of Physics or Foundation of Physics and Physics lectures, and so on. So all the results that I'm going to present are peer-reviewed. So I want to give a premise because to avoid misconceptions here, and I introduce the idea in terms of the wave-particle duality as it was introduced by de Broglie 100 years ago. So we assume the existence of a certain periodic phenomenon, say of period T, capital T, which is to be attributed to each and every isolated energy parcel of energy. So the periodicity and the energy are related by the Planck constant. Now, I want to bring this de Broglie statement to its extreme consequences, a little like Einstein did with the constancy of the speed of light. So I postulated that every isolated system of energy E is a periodic phenomenon of intrinsic periodicity T, given by the Broglie relation. And okay, where is the difference with respect to the de Broglie statement? So if we consider now we are concerned about isolated system, okay, nobody can say that this is wrong because we are using this idea since a century ago, and actually all zero temperature physics is characterized by some kind of periodicity. By the way, where is the difference? Okay, if we consider classical mechanics, okay, the Newton's first principle of inertia, we had that every free isolated particle of constant energy E is moved in straight lines. And with de Broglie, with ondulatory mechanics, we have that every free isolated particle of constant energy E is a periodic phenomenon of persistent periodicity T, where this periodic phenomenon is meant to be a monochromatic wave. Now, the difference is that now we assume that every isolated particle of constant energy E is a periodic phenomenon constrained to have persistent periodicity. That is, it is an harmonic system or like a vibrating string in time. Essentially, if we have the yellow one is the de Broglie monochromatic wave, we will allow a timbre to the de Broglie wave. We will allow all the harmonics consistent with the underlying periodicity. So we essentially have described sound or a vibration along the time dimension. And this naturally corresponds to a quantized frequency spectrum, which is in physics is a quantized energy spectrum. Or the other way around, a quantized energy spectrum would mean we have the suspect that it's something vibrating in time. Okay, and So another way to visualize this idea comes from the Einstein definition of relativistic clock. A clock is a phenomenon passing periodically to identical phases. So all that happens in a given period is identical with all that happens in an arbitrary period. So we will also represent these elementary systems that we are going to describe as elementary clocks. So we can rephrase these answers by saying that every isolated system of energy is an elementary clock of intrinsic periodicity. And we will use this to visualize some concepts here. Okay, but this doesn't mean that everything in the universe is periodic, as much as in the Newton first principle doesn't mean that everything moves in straight lines, because this is only true in the very particular case of isolated systems. But even if we consider a periodic phenomenon, that is a periodic phenomenon with persistent periodicity, where the periodicity is always the same along the evolution, and we consider two or more of these, we have an ergodic system. Then, if we consider that the energy and the periodicity are two faces of the same coin, they are related by the Planck constant, they are both dynamical quantities, local quantities, we find a picture that is more complex. So if we imagine a system interacting and passing from low energy to high energy, that is from long periodicity to short periodicity, okay, and we see that we can establish a before and an after the interaction, and so we understand that we will have causality, but what we are describing is essentially in the analogy of a violin string, where the player can modulate the string length and generate complex melodies. In the same way, periodic phenomena evolving and interacting modulates their periodicity. So this is a dynamical picture, is not a naive description of periodicity. And if we put together an ensemble of periodic phenomena interacting each other, so the picture is similar to an orchestra where the complex combination of locally modulated harmonic systems, the musical instruments here, can generate any complex symphony. So modulated harmonic systems can reproduce the whole complexity of nature in principle. Okay, after the premise, we go through the main, the more general result that I have recently published here. Is for any generic Hamiltonian system, it is a very symplectic manifold, and this includes Minkowskian manifolds, pseudo-Riemann manifolds, and infinite dimensional manifolds. Okay, the statistical description of the classical harmonic mechanics resulting by imposing intrinsic time periodicity is fully equivalent to the quantum mechanics resulting from the canonical quantization of the system. I want to say something about periodic boundary condition in times, because we have experimental evidence of a system that satisfies periodic boundary condition in time. These are the time crystals. And furthermore, every time that you observe a particle in a box in a reference frame, which is not the one of the box, since the relativity mixes space and time, we must describe together with the boundary condition on the spatial dimension, also boundary condition along the time dimension. So, and in this way, we obtain, giving the harmonics to the de Broglie wave, we obtain equivalence with quantum mechanics. The setup of this theorem starts from, okay, the principle of the least action. So in the ordinary classical mechanics, we have a generic action and we minimize this action. So the bulk term of this variation gives us the equation of motion, the Euler-Lagrange equations. And the boundary term, now we must vanish the boundary term, and typically we impose what I call here the synchronous boundary condition. So we assume that the variation are zero at initial and final time. In this way, we select a solution, say, of energy E1 at time t. Now we want to do something similar. So allow me to replace the initial time and the final time with a generic Tx and Tx plus capital T of x. So we minimize this action. So we have the equation of motion, the same one of the classical, ordinary classical mechanics. But now we want to minimize this boundary term by imposing periodic boundary condition. We know from string theory and extra dimensional theories that this is a consistent way to minimize the boundary of the action, and together with Dirichlet and Neumann boundary condition and so on. But okay, if we impose this periodic boundary condition, we select a class of classical solution where, okay, which are is a harmonic system, and this doesn't correspond to a single energy, but it corresponds to a energy spectrum. So we have a perfect analogy with the classical phase, and this is classical mechanics. And so the energy spectrum comes directly from those two equations. And so technically, we are saying that we are a cyclic dimension. So we are rolling up the time dimension. But this doesn't mean that we are limiting the solution inside this time interval, because we can extend the solution to every time. So like in the ordinary classical mechanics, we are selecting a solution with energy, with a given energy spectrum. Actually, the fact that we are minimizing the action of the boundary, and we want always satisfy this, is the fundamental reason for the full consistency of the work construction that we are going to describe. And this can be seen by the fact that this is the Stokes lemma. So that means that the time periodicity form a vortex tube along the system evolution, so that this condition which is essentially the Brownian condiction, is always satisfied for every time along the time evolution. If of course, the time period must evolve according to the Hamiltonian flux here. And for the sake of simplicity, we match the solution of the classical system with the frequency of the fundamental mode of this harmonic system. So now the line of the demonstration involves Hamiltonian mechanics, and so we have a phase space of classical solution, and we impose intrinsic periodicity by means of a Dirac constraint, an Hamiltonian constraint, so in order to impose intrinsic periodicity in times. And the periodicity, whenever we impose intrinsic periodicity in time, we have a periodicity space through the equation of motion. So, and this is, of course, the ordinary de Broglie wavelength. And okay, so we impose intrinsic periodicity, we project the solution, the classical solution, into a reduced phase space of the harmonic classical solution. And we can introduce this ket here, we project the solution into the harmonic solutions. And that is described by this form, the Hamiltonian constraint. And we realize that this is the final Hilbert space, because the harmonics here of this system forms an infinite base for the Hilbert space. So actually the Hilbert space was introduced for a historical reason to describe harmonic systems. And okay, so the quantization condition is the Weyl integrability condition, which is a fundamental ingredient for geometric quantization. Now the consistency condition for the Hamiltonian constraint is the Schrödinger equation. And then we have something non-trivial here, because the non-trivial topology of the theory that we obtain by the positive periodicity implies that we have a gauge invariance. So in other words, when we have this circle, we are using this notation, and this is a very comfortable integral where the integral interval vary from point to point. So if we try to write the same equation in terms of an integral with constant integration interval, we must introduce a covariant derivative. So the difficult part of this demonstration is to find the correct form of the momentum and position operator in this reduced space. And eventually we obtain the same operators of ordinary quantum mechanics, but then they can be written in terms of covariant derivatives. So we can apply the result of geometric quantization, solving also problems of geometric quantization, because now the degrees of freedom are reduced to half because the momentum and the energy is fixed by the boundary conditions. So, and we obtain all the Dirac solutions. So the commutation relations essentially is an indirect way to say that we are imposing intrinsic periodicity in time and space. And the constraint on intrinsic periodicity is a quantization condition fully equivalent to the canonical quantization for all possible, also this is true for the Minkowski manifold and the Pseudo-Riemann manifold and infinite dimensional manifold. Okay, this is mathematics, so it's not very intuitive. We can easily understand what happens here if we consider a free system, which is an harmonic system, an homogeneous harmonic system like a vibrating string. And this would be soft cellular automaton. So we have a system constrained to have a given periodicity. So this is a harmonic system where the harmonics define an Hilbert space, which is the natural application of Hilbert space. The Hamiltonian operator is essentially a frequency operator multiplied by a time constant, and the harmonic system is a state in this Hilbert space. And we have a wave equation, wave evolution. We have the Schrödinger equation. So is this equivalent to quantum mechanics? So to prove that, we want to find once again the commutation relation of quantum mechanics. So now if we try to evaluate the expectation value of a total derivative, and for the sake of simplicity, we integrate over a single period here, but this is not limiting hypothesis, say. Or when integrate by part, we have a boundary term, and when integrate on the left and right side, we have this term in terms of the momentum operator, which comes in an analogous way. Here, we do the same along the spatial dimension. So we must conclude that every time we impose the commutation relations of quantum mechanics, we are saying that the spatial or the time variable is a cyclic variable. Here it must be periodic in order to obtain the commutation relation of quantum mechanics if we believe in mathematics. Okay, can we observe this cyclic natural spacetime from the Feynman path integral? Yeah, the answer is yes. And we can prove this identity in two different independent ways. And so we have that the ordinary Feynman, this is the illustration is for a single degree of freedom, okay? But we find that the ordinary Feynman path integral of quantum mechanics can be written as a sum of a Dirac delta, that is of a path. But these paths here are all the possible classical paths with different 1D numbers that links to arbitrary points, initial and final point on a cyclic geometry. Essentially, this path here, the Feynman path integral, is the sum over the solution of our theory. Now it's written in terms of the Lagrangian density. They are basically put the space-time periodicity. The circle here means that I am assuming periodic boundary conditions. And so the Feynman path integral is the interference of classical paths. All these paths are solution minimize these action defined in cyclic space-time. We can understand this result in a more easier way if we consider the three things. Or actually, this is something evolution like a cellular automaton, okay, in the proper time, okay. But if we consider a free system, which is has a persistent periodicity, now we have an homogeneous cylinder here. We can imagine to cut and open this cylinder. So all these cyclic paths are these light blue lines. Since the evolution is manifestly unitary because we are using periodic boundary condition, we can cut and pass the translate by period the red green lines and obtaining a path with the same initial final point if we rearrange these paths together. And if we repeat this, if we iterate this process many times, we find that all these cyclic paths can be represented as variation around a given classical path, but this variation anyhow comes from classical path. They are classical paths. Okay, and so we have the we can also prove this equivalence, this correspondence in the second quantization, because if we consider an harmonic oscillator and we impose the natural periodicity as a constraint to this harmonic oscillator, okay, we are showing derivation in the space and the harmonic spectrum. So, but is this equivalent to the ordinary quantum harmonic oscillator? We have to prove the computational relations of quantum mechanics. Now we assume generic computational relation here with delta in a complex number, and we use the Schrödinger evolution here. So if we impose intrinsic periodicity, the condition of periodicity, the only possible choice is the commutator of quantum mechanics, ordinary quantum mechanics. And the same for the Fermi oscillator, we have the same commutator of ordinary quantum mechanics. So now, if we consider a field, a classical field, which is the integral of the field modes of fixed period, so every mode with constituting the field is like the note in a grand piano, where the system, if we impose intrinsic periodicity, the system is an harmonic system. And okay, we obtain the energy spectrum of second quantization, and we find that, again, the second quantization of the field is equivalent to impose the natural periodicity as a constraint to each field component. And we have also something interesting here that we can see from this graph. The proper time periodicity, which is a consequence of the Einstein relation and the Bloom relation, is the mass is a proper time periodicity, okay, which fixes the upper limit of the periodicity of a particle, and the heavier the particle, the faster the periodicity. So every particle at rest is a reference clock ticking at quantum time, and these are incredibly fast. While the massive particle is a frozen clock, so the periodicity at 0 momentum tends to infinity. Okay, here we have a representation of the black body radiation, because now every component of the electromagnetic fields is like a vibrating string in time with all possible harmonics. So we have the Planck energy spectrum with the classical and quantum limits. And so again, Fourier looked into this spectrum will say that there is something periodic in time. The time dimension is something compact and cyclic. Okay, now the Compton time set the upper limit of this periodicity, and every experiment involves electron and electromagnetic waves. So even if we consider an electron, which is the lighter particle of the standard model, except neutrinos, but neutrinos are difficult to observe, okay? We find that the electron Compton time sets the lower limit of these intrinsic, the ultra-sparse dynamics. And the Compton time of the electron is far away from the experimental resolution in time that we have, as we know, for instance, from this year Nobel Prize here. So every system is characterized by, composed by elementary particles, is characterized by periodic dynamic faster than 10 to the minus 21 seconds. So every particle, elementary particle, is like a die, and dice is rolling too fast. In dice rolling too fast, the outcomes can only be predicted statistically. So we are, according to our result, quantum mechanics are periodic dynamic, comes from periodic dynamic, but these periodic dynamics are extremely fast, ultra fast, and we can only describe this periodic dynamic in a statistical way, like we do for dice. So that the system is like a particle moving very fast on a circle here. So if we think to the electric current, when we have many particles moving on a circuit, or we adopt a statistical description with a current density, because we have the description of single electrons. But this is true also if we have a single particle moving very fast on a circle, if our time resolution is too low with respect to the time in the characteristic time of this particle inside the circle. So again, we can adopt a statistical description with the condition that now we have a single particle in the whole circuit. So we have something which is something Born rule. In all this description, we are not introducing any fine-tunable parameter, and this is something unusual in theoretical physics, but is a positive aspect for sure. But okay, for sure, we are not introducing any hidden variables. So we have the Bell theorem cannot be applied here. Now, if we consider the relation of the Bell's inequality, okay, we consider observable that only can take plus and minus values, and we consider this a combination of this observable, and we want to evaluate the expectation value of C squared, which can be written in terms of commutators. And we know that in ordinary classical mechanics or classical mechanics involving hidden variables, these must be less than 2. This is the ordinary Bell's inequality. But in quantum mechanics, we postulate that we have the commutators are different from 0, and so we have a violation of Bell's inequality. But now we have proven in many different ways that the commutation relation and quantum mechanics is a direct consequence of the intrinsic periodicity, the condition of intrinsic periodicity. So by the principle of logic, we must say that if B implies C and A implies B, then A, intrinsic periodicity, necessarily implies that C, a violation of Bell's inequality. So I'm trying to work on a microscopic example of this violation, but in any case, I think that the solution of this riddle will be the following one. So, according to Bell, if Bell would try to interpret this identity, the condition of intrinsic periodicity, Bell will say that it is a non-local relation, a manifesting non-local relation, because what happens at time t happens at a later time or at a later or a different wavelength. So the same is for along the spatial dimension. So, okay, so Ben is right. Quantum mechanics comes from non-local aspects of physics, but which is classical, by the way. Also, Einstein, at the same time, would say, oh, this relation of intrinsic periodicity describe a relativistic clock. As we will see in a moment, this actually describe a relativistic clock, whose evolution is modulated by interaction, so that we can establish a before and an after the interaction. So it seems to me that this approach finally conciliates Bell's and Einstein ideas about this foundation of Bell's inequality. And okay, I skip this, but of course we have the non-relativistic limit of elementary particles. We have the Heisenberg uncertain relation, because the Heisenberg uncertain relation is a consequence of the commutation relation, essentially. We can describe any textbook quantum problem here, because we have a generalization of the boson for quantization condition, and of the same for the atomic orbital. So the fact is that nobody is surprised when we say that the angular momentum is obtained by imposing a periodicity in the spheric angles. So this is with topology X2, and these are the atomic, the spheric harmonics. But now we have the same. We obtain the quantization, the principal number of the atom was saying that the electrons must have closed orbit in space-time, and which doesn't mean that are circular orbit. Okay, they can have any form, but the important requirement is that the electrons around a nucleus has a closed orbit in space-time. And so we obtain the quantization of the energy exactly as we obtain the quantization of the angular momentum. This is an example of a non-harmonic spectrum, because now this harmonic system is on a Coulomb potential. So, but we have the Bohr atom. Now, if I have 10 minutes, I would like to show how it's possible to get a gauge interaction from the principle of covariance, similarly to gravity. Because if we want to introduce interaction in a non-perturbative way in this theory, we must somehow deform the periodicity of. So we start with an isolated system with persistent periodicity. The periodicity are always the same, so we deform this periodicity in order to obtain locally modulated harmonic system. We can do this by means of local transformations, and so we assume this transformation variable in the free case. So we are local deformation of the matrix, and this corresponds this substitution of variable in the free periodic harmonic system correspond to deformation of the matrix, and but together we have that the periodicity, the boundary of this action vary from point to point, which corresponds to the fact that now we are modulating the solutions of this action. And to the Planck constant, this corresponds to describing interaction, so a local variation of the form momentum. Of course, this is the same description of gravity, because we can assume, for instance, a Varshik potential. So we describe the modulation of the flux and of the ruler inside a gravitational potential. And so in this way, we are describing gravitational interaction. But there is a new possibility, which is only possible in this particular non-trivial topology that we are obtaining by imposing intrinsic space-time periodicity. And this is the fact that even if we assume a local isometry, so we have this transformation of coordinates, but now we pass from a flat space-time to a flat space-time, okay? This transformation of coordinate is inside the free system, harmonic system, correspond to a theory in flat space-time, but now the boundary is locally rotated. So we are rotating the boundary of this theory in flat space-time. And this is only possible because we have a non-trivial topology now. And okay, these of course correspond to a modulation of the solution. So we are describing interaction, even though we are in flat space-time. And so the Planck constant, this corresponds to a local variation of the form momentum, which can be written in the typical form of the linear substitution of electromagnetism, which is sum of the U1. Okay. Oh, but again, it's very uncomfortable to work with an action where the boundary vary from point to point. So if you want to try to take the same action, so the same system with the same solution in terms of an action whose boundary is constant, always the same, we must introduce a covariant derivative, and the covariant derivative is the same covariant derivative of ordinary electromagnetism. So we have the tuning, the modulation is described by the parallel transport and the Wilson line of ordinary electromagnetism. But now, okay, we have here we can also introduce the Yamik terms because it's stage invariance, so it's there. But now we have the fact that the periodic boundary condition represented by this circle in this theory will describe quantum electrodynamics. If we actually consider all the harmonics and the interspace, and we evaluate the evolution of all these harmonics, we find that the evolution of this harmonic system is again given by the ordinary Feynman-Patin integral of quantum electrodynamics for a single degree of freedom. Okay, so okay, here we have something also very interesting, because in general, the result described the general result, the general theorem presented before, say that periodic boundary condition quantize the interaction for all generic harmonic Hamiltonian systems. So the periodic boundary condition now describe the quantization of this generic interaction scheme. But the same should happen also for gravity. I mean, now also gravity should be defined in a compact space-time. So we have this periodic boundary condition in the action, gravity action. And so according to our result here, so this will describe quantum gravity, but I want to understand better this point, of course. By the way, we have another interesting aspect here that according to Rovelli, statistical mechanics and the equilibrium thermodynamics suggest the existence of internal times if applied to general relativity. So our description of particles in terms of elementary space-time cycle actually seems to realize this idea of internal times, and these are something that is good for gravity and a possible theory of quantum gravity. Now, if we impose intrinsic periodicity to this solution here, we immediately find the Dirac quantization of magnetic monopoles here. And from this, we have all the phenomenology of superconductivity, including just some effect. Because if we can, now we have we impose intrinsic periodicity, and here we have a Goldstone. We find that the Goldstone can only vary, is periodic, and can only vary by finite steps. So the magnetic flux inside a superconductor can only vary by finite quantities. and this means that we have zero resistivity. We find also that the Lagrange at the junction of two superconductors can only depend on the phase difference of the two Gaussian fields. So F here is a periodic function, and we have the A, C, and the C just some effect, and the Meissner effect as well. And I want to say something also about the temperature. And so if we consider the thermal time is the typical time of the quantum noise. So the Minkowskian time here is represent perfect periodicity. The Euclidean time is the opposite, is a damping factor. So if we consider a system at low temperature, so that the typical time of this harmonic system is small with respect to the thermal noise. So this harmonic behavior can autocorrelate. So we have a harmonic system. But if the temperature is high, so that the thermal noise is very fast with respect to the typical time, quantum time. So the system cannot autocorrelate. It is like a grand piano. If you try to play a grand piano in a very noisy environment, so that prevent the formation of sound inside the piano strings. Also, we have something interesting here because we know from Matsubara theory that the quantization of statistical systems involved or is a periodicity in the Euclidean time, and this was believed to be a mathematical trick. But now, okay, this seems to be a particular case of or general result where the quantization of elementary system is obtained by imposing time periodicity. Okay, here I think I can skip this, which is a okay. I just mention another result that the same answers provide somehow we can prove that the ADS CFT correspondence, so the fact that any classical configuration extra dimension has a dual interpretation in quantum four-dimensional conformal field theory, we can prove that this relation is a mathematical identity, and this is proven in this paper here. So a few conceptual concepts, comments here. So just okay, if we know for sure that the universe is composed is described in terms of elementary particles, but every elementary particle is a periodic phenomenon. We are using this hypothesis since the beginning. So the natural consequence of these two facts is that physics can be consistently described in terms of periodic phenomena. And actually, we do this implicitly every time we use observatory mechanics in quantum mechanics. We are saying that physics is described in terms of periodic phenomena. Then we have the time, also the time axis here is defined in terms of a periodic phenomena, in particular in terms of the atomic clock, which is a periodic phenomenon. So time, so what we get is that actually we can drop the external time axis and describe physics in terms of these periodic phenomena. And time, so time as a cyclic method whose manifestation is the work plethora of quantum mechanics. So the picture is this, where the red clocks is the background cosmic radiation, very long periodicity that is the ground space-time where the particle moves. And okay, so we find a description where the law of quantum mechanics, the obscure law of quantum mechanics, and that seem to put a constraint to our knowledge of nature now is described by the most beautiful law of physics, which are the law of harmony and sound, because the whole theory described so far is essentially the theory of sound, the relativistic generalization of the theory of sound, where objects cannot only vibrate in space, but they can only vibrate in time. And so we have a very fascinating description of nature based on the law of harmony. And how could it be different, I would say. Now, the sad part of this story, because in more than 10 years, arXiv has censored all my 20 papers on the subject. And this is probably the reason why nobody knows about my work. And so you can read my essay here, the name of the arXiv. And this because my papers are hidden in this secret room of the arXiv library, which is the category physics, general physics, which is used by arXiv as a tag to downgrade ideas. And so, of course, nobody put people on the stack today, but censorship today is to add defamatory tags to ideas. And actually, in this for this respect, arXiv behaves like an inquisition tribunal with an archival very sense of the scientific method without giving a motivation on the merit of papers and so on. So I conclude my talk here because by assuming, by postulating and bringing to its extreme consequences that every isolated system of energy E is a periodic phenomenon of persistent periodicity T, and nobody can say that this is wrong because we are using this idea since century, since 100 years. We obtain a full mathematical unified description of quantum mechanics and classical relativistic mechanics. Quantum mechanics is a manifestation of a cyclic topological non-trivial space-time fully consistent with relativistic causality. We have a prediction of new possible deterministic physics beyond quantum mechanics, possible a new approach to quantum gravity, and a unified, a common, I would say, mathematical description of the interaction in gravitational interaction in terms of the principle or relativistic covariance, and much more, because this is really a Pandora box when, if you want to have fun with this theory, you will see result popping up in the most beautiful way. So, and please, I need support because this story is becoming bigger than me. And okay, thank you. Hello.